At 3:36 UTC on May 16, 2026, sensors aboard the Discover spacecraft positioned between the Earth and Sun recorded solar wind moving at 823 km per second, a wall of charged plasma traveling at 2,962,000 km per hour, carrying within it a magnetic field. So compressed and so erratically oriented that it drove Earth's geomagnetic environment into G2 moderate storm conditions within hours. By the morning of May 17th, as you watch this, the UK Met Office confirms that wind speeds remain elevated at approximately 630 km per second, still classified as strong, sustained now across more than 30 consecutive hours, with NOAA's Space Weather Prediction Center forecasting G1 minor conditions continuing through this day. If you rely on this channel for science-grounded and verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA, the UK Met Office, the Smithsonian Global Volcanism Program, NASA, and peer-reviewed research published in journals including PLOS One and the Journal of Space Weather and Space Climate. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public. The responsibility to check belongs to all of us, but that is not even the complete picture, because the solar wind battering Earth's magnetic field this weekend did not arrive from a solar flare, the kind of explosive event with hours of warning that space weather forecasters can at least partially anticipate. It arrived from something older, quieter, and in some ways more unsettling: a large trans-equatorial coronal hole, an opening in the Sun's outer atmosphere where the magnetic field lines do not loop back on themselves but instead extend outward into space, releasing solar wind at velocities far beyond the typical 400 kilometers per second of the ambient slow wind. NOAA's own documentation states that coronal holes produce solar wind ranging from 500 to 800 kilometers per second. This stream reached the upper boundary of that range and then exceeded it, peaking at 823 kilometers per second, the kind of figure that, when you hold it still for a moment, begins to do something to your understanding of distance and force. 823 kilometers per second, that is the speed at which a volume of ionized hydrogen and helium, electrically charged and threaded with magnetic field, struck the first line of Earth's defense, the magnetosphere, at a sustained rate across an entire planetary rotation. To give that number a shape you can stand next to, a commercial aircraft travels at roughly 0.25 kilometers per second. The solar wind arriving at Earth this weekend moved at approximately 3,300 times the speed of that aircraft. It covered the 150 million kilometers between the Sun and Earth in roughly 2.5 days, and it did not stop when it hit the atmosphere. It pressed and compressed and pushed the magnetopause, the boundary between Earth's magnetic field and interplanetary space, inward on the day side of the planet, squeezing a protective structure roughly 65,000 kilometers thick into a fraction of its usual depth. What the official data actually shows is this: on the night of May 15th going into May 16th, geomagnetic activity reached G2 moderate storm levels on NOAA's 5-point scale, with KP indices reaching 6. The interplanetary magnetic field strengthened to strong levels. The B's component, the north-south orientation of that field, swung south, and when it does that, it opens a door. A southward B's aligns anti-parallel with Earth's own magnetic field, allowing magnetic reconnection, the transfer of energy from the solar wind directly into the magnetosphere. This is the mechanism that generates geomagnetically induced currents in the ground and in the long metal conductors running across it, power lines, pipelines, rail infrastructure, the physical backbone of industrial civilization. And here is where this account becomes genuinely significant, because this is not a hypothesis. This is documented in the geological record and in the engineering record both. On March 13, 1989, at precisely 7:45 Universal Time, Hydro S735 kilovolt power grid collapsed, not gradually, not with warning sufficient for intervention. The James Bay network went offline in less than 90 seconds. The storm responsible, the result of a coronal mass ejection on March 10th and a second CME on March 12th, driven by an X-15 class flare on March 6th, produced a geomagnetic disturbance that reached extreme levels, classified today as among the strongest of the space age. The telluric currents it induced, direct currents flowing through the Earth and finding their way into transmission infrastructure, overwhelmed the static compensators at Chibougamau substation. Circuit breakers tripped. The imbalance cascaded 150 kilometers down transmission lines. Within 1 minute, 21,000 megawatts of generating capacity went offline. 6 million people in the province of Quebec found themselves in darkness, not for minutes, for 9 hours. The temperature in Quebec on the night of March 13, 1989, was well below freezing. 6 million people. No heat, no light, no information. They heard nothing, not because the authorities were hiding anything, but because the grid that powered the communications infrastructure had also gone dark. In those 9 hours, over 200 separate grid faults were recorded across the continental United States as the same geomagnetically induced currents reached southward through interconnected networks. A 500 kilovolt transformer at the Salem Nuclear Generating Station in New Jersey sustained damage from GIC stress alone. Not from any physical impact, not from any human error, but from invisible direct current saturating its core and heating it beyond its engineering tolerances. The total material damage to Hydro alone reached $13.2 million. Quebec subsequently spent $2 billion over 6 years hardening its grid against a recurrence. The question is not whether this can happen again, the question is when. Think for a moment about the people in the path of what is happening right now. The city of Troms, Norway, sits at 69 degrees north latitude, well within the auroral zone, the belt of sky where geomagnetically induced currents concentrate and where the ground beneath high-voltage transmission infrastructure is electrically resistant Precambrian rock, the same geological condition that made Quebec so vulnerable. In 1989, Troms has a population of approximately 77,000 people. Tonight, May 17, 2026, with G1 conditions persisting and the high-speed solar wind stream still flowing strong, those 77,000 people may look up and see the aurora borealis shimmering above their city, green and violet curtains draped across a sky that is simultaneously beautiful and conducting the same currents making that sky glow are threading themselves through the power lines that heat their homes, power their hospitals, and keep their communications infrastructure alive. They do not know what voltage their transformers are accumulating. Neither, in real time, does most of the world's grid infrastructure have sufficient monitoring to tell them. This is not a statement of alarm for its own sake. This is the verified finding of a 2025 peer-reviewed study published in PLOS One, authored by Figueroa, Acevedo, and Porta, which examined U.S. Department of Energy outage data from 2006 to 2023 against NASA OmniWeb solar wind parameters. The conclusion was statistically unambiguous. Years with a higher count of geomagnetic storms, particularly those with multiple strong or severe events, exhibit elevated incidences of unexplained power interruptions. The correlation between increasingly negative DST values, enhanced solar wind velocity, and outages attributed to unknown causes was confirmed. A simple regression model in the same study identified storm intensity and average magnetic field strength as statistically significant predictors of unexplained outages, more predictive than sunspot number alone. The system is not inactive, it is accumulating, and what makes May 2026 a moment of particular scientific attention is not any single storm, it is the position of solar cycle 25 in its arc. In December 2019, an international panel convened by NOAA, NASA, and the International Space Environment Services predicted that solar cycle 25 would be a weak cycle, peaking at a smooth sunspot number of 115 in July 2025. That prediction was wrong. Solar cycle 25 peaked in October 2024, at a smooth sunspot number of 161, 40% above the original projection. The monthly mean sunspot number reached 216.0 in August 2024, according to data published in the Journal of Space Weather and Space Climate. Solar activity, as gauged by the frequency and intensity of solar X-ray flares, was described in that same publication as intense across the whole of 2024. Solar cycle 25 is not weakening on the schedule that was originally modeled. The descending phase of a cycle that already exceeded its forecast is producing elevated CIR activity, correlating interaction regions, the compressed walls of plasma that form where fast solar wind overtakes the slower ambient wind. Unlike a coronal mass ejection, which erupts suddenly and can arrive with as little as 18 hours of warning, CIRs are a predictable feature of a rotating sun with persistent coronal holes. NOAA flagged the incoming stream behind this weekend's storm as early as May 13th, 4 days ago, which is precisely the kind of advance warning that separates a managed disruption from a catastrophe, provided the people who receive that warning have the infrastructure to act on it. Most of the world does not. The North American electric power grid comprises more than 200,000 miles of high-voltage transmission lines, thousands of generating plants, and millions of digital controls owned and operated by more than 1,800 separate entities. It is, by design, interconnected, and that interconnection is both its strength and its fundamental vulnerability. The same linkages that allow power to flow from a surplus region to a deficit region also allow geomagnetically induced currents to propagate across jurisdictional boundaries at the speed of electricity itself. The Salem transformer in New Jersey failed in 1989 not because New Jersey was close to the epicenter of the storm, but because the grid it was connected to stretched from Atlantic provinces to the American Midwest, and the induced currents moved along it without asking permission. Extra high voltage transformers, the 500 kilovolt and 735 kilovolt units that form the backbone of long-distance power transmission, cannot be quickly replaced. They are typically manufactured overseas. Procurement cycles range from months to years. A sufficiently large geomagnetic storm, one producing GIC amplitudes not at the levels seen this weekend but at the levels recorded during the May 2024 event when DST reached negative 420 nanoteslas and GIC neutral currents exceeding 30 amperes, were recorded in Latin American power networks at Laguna Verde and Riviera Maya, could damage transformers faster than the global supply chain could replace them. The May 2024 storm was described in peer-reviewed literature as the most intense geomagnetic event since 2003. The 1989 Quebec storm was described by Dr. David Bottler, head of the spaceweather group at Natural Resources Canada, as the biggest geomagnetic storm of the space age. Both of those events are now in the past, they are in the record, and the record shows that they were not the upper bound of what the sun is capable of producing. In September 1859, a solar storm now known as the Carrington event produced auroras visible at tropical latitudes, induced currents strong enough to set telegraph paper on fire, and caused spontaneous sparking in telegraph equipment across Europe and North America even after the machines were disconnected from their batteries. The solar wind speed during the Carrington event has been estimated by researchers at between 1,000 and 2,000 kilometers per second. The solar wind measured at Discover on May 16, 2026, peaked at 823 kilometers per second. That is not the Carrington event, but it is in the same order of magnitude as conditions that, in 1859, operated on a world without a single kilometer of high-voltage transmission line, a world that had nothing to lose but its telegraph wires. The world in which that same sun now operates has 200,000 miles of high-voltage transmission infrastructure in North America alone. Scientists choose their language carefully here, and that careful language is itself the warning. NOAA does not say that geomagnetic storms will cause blackouts. It says that G4-level storms produce possible widespread voltage control problems and that some protective systems may mistakenly trip out key assets from the power grid. That construction mistakenly trip out key assets is the language of engineering documentation. Translated into the language of consequence, it means the safeguards designed to protect the grid may interpret a geomagnetic disturbance as a fault condition, and in responding to something that is not a conventional fault, they may create one that is. This is precisely what happened at Chibougamau in 1989. The protective relays did exactly what they were designed to do. The result was 9 hours of darkness for 6 million people. The GOES-19 satellite, operated by NOAA, is currently imaging the sun in extreme ultraviolet wavelengths. As of May 16th, it captured a massive trans-equatorial coronal hole facing straight at Earth, the source of this weekend's high-speed stream. That coronal hole has not closed. The sun rotates approximately once every 27 days. If the coronal hole persists through the next solar rotation, Earth will pass through its outflow again in approximately 3 to 4 weeks. NOAA's SWPs will be watching. The CNLIL model, a large-scale physics-based simulation of the inner heliosphere, will attempt to forecast the arrival window and intensity. Satellites at the L1 Lagrange point, including Discover and the newly positioned SUFO L1 observatory, which completed its final orbital burn on January 23, 2026, will provide real-time measurements as the stream approaches. Monitoring is in place. Detection is possible. Prediction, however, is not certainty. The coronal hole that produced 823 kilometers per second did not require a solar flare. It required only a region of open magnetic field on a sun that is still in the elevated descending phase of a cycle that already exceeded its forecast by 40%. The science of solar prediction is improving. The technology of space weather observation is improving. The hardening of power grid infrastructure against geomagnetically induced currents is improving slowly, unevenly in some jurisdictions and not others. Consider the 77,000 people of Troms again. Consider the 40 million people of the state of California, whose grid infrastructure stretches from the Oregon border to the Mojave Desert along a north-south axis, the orientation most vulnerable to GIC loading. Consider the 3 million people of New York City, whose power flows through transformers that in 1989 were already absorbing enough induced current to begin thermal degradation. Consider every city, every hospital, every water treatment plant, every data center whose operations depend on continuous power that arrives through lines strung between towers, through transformers connected to a grid that was never designed with the sun in mind as an adversary. The star at the center of this solar system has been active for 4-6 billion years. It has been producing high-speed solar wind for longer than there has been life on the surface of the planet it illuminates. The instruments we use to measure it have existed for decades. The infrastructure we have built in its path has existed for a century. The alignment of those three facts, a sun older than imagination, instruments newer than memory, and infrastructure that lies between them, is not a coincidence. It is the precise geometry of a risk that has already materialized once, in Quebec, on a March night in 1989, when 6 million people spent 9 hours in the dark wondering what the sun had decided to do, and no one had a good enough answer to give them. The solar wind speed, as of this morning, remains at approximately 630 kilometers per second.